Hi, my name is Aidan Lytle, and I will be talking about combinatoric modeling of flow and non-flow in relativistic heavy ion collisions, which is my project with Dr. Ron Belmont over the past year. What we're going to be talking about is, first, what are relativistic heavy ion collisions? Second, what are we testing? Third, what are our models? Fourth, what do they tell us? And fifth, what's next? Relativistic heavy ion collisions are important because they take two nuclei accelerated at nearly the speed of light, smash them into each other, and create something that is remarkably similar to the state of the universe directly after the Big Bang. This is called the quark-gluon plasma. It is a fluid state of deconfined quarks and gluons. And we can recreate this in the lab consistently. The goal of our field, heavy ions, is to create, identify, and study the quark-gluon plasma. Relativistic heavy ion collisions have important measurements that need to be understood. One of those is azimuthal anisotropy, which is some of the measurements of the flow of this fluid. The hydrodynamic, which is basically the hydrodynamic translation of the initial shape into the final shape distribution. It can be represented as a Fourier series, which a standard representation of is here, and what our format is here. We want to show how this changes with respect to multiplicity. The fluid flows, as you can see here, from higher pressure to lower pressure regions, and the pressure gradient is proportional to the thickness of the circle, these outer nuclei shell, about the overlap bounds. So, some more definitions. Flow correlations are independent of the number and multiplicity of particles because all particles are affected. Non-flow refers to all other correlations, notably those that depend on n. The number of k tuplets in a collision with n particles is n divided by k. And the reasoning for that is if I have n things and I need to find how many sets of k things there are in that set of n things, I need to divide it by k. Experimentally, we don't know which particles are correlated with each other. We must check all possible combinations of k particles, of which there are n choose k. Combinatoric dilution refers to the fact that the measured strength of the non-flow correlations is reduced relative to the intrinsic strength because there are more possible k tuples than there are true k tuples. As a demonstration, our hypothesis is that non-flow correlations will be reduced by a factor of n divided by k, or the number of true correlations, divided by n choose k, or the number of total correlations, or number of total possible correlations. This reduces, when n is very large, to about k minus 1 factorial over n to the k minus 1 through various combinatoric maths. Binary correlations, another important definition, are defined by a function that returns a value of 1 if and only if all k particles are correlated and a value of 0 otherwise. The combinatoric function describes binary correlations perfectly. And data converge to the approximate power law from a form at large n, shown in several of our figures, using a binary correlation generated collision where k is equal to 2. The general form of the k-particle correlator is this. Notice the absence of psi rp. Since we're studying the angular correlations of multiple particles, the psi rp cancels. The correlators of interest for this study are 2, 4, 6, and 8. What are our models? On to that important question from the beginning. We developed a Monte Carlo generator to study the combinatoric dilution of this k-particle correlator. To generate one k-tuplet, we choose a random angle phi between negative pi and pi. We generate a second angle exactly pi radians away from this phi. We generate additional angles close to this initial angle and generate additional partner angles pi radians away from these. This can be repeated n divided by k times to recreate an n-particle collision and mimics conservation of momentum and maximizes n equals 2 correlations. All calculations use n equals 2. And repeat this as desired to generate the statistics we need. The Monte Carlo k-particle correlator results follow a combinatoric dilution of the power law of k over 2 instead of k minus 1. The simple binary correlation gives exactly the expected combinatoric dilution. With a large n limit, the binary correlation function follows a power law behavior with a power of k minus 1. The combinatorics of the k-particle flow correlator behave differently. This gives rise to asking, what are the underlying combinatorics of the k-particle correlator that give rise to the power of k over 2? We hope to improve our understanding of the combinatorics with higher statistics and some analytic methods here, as well as using a particle event generator named Pythia. In the future, we plan additional studies with an event generator called Pythia that has a wide variety of realistic physics processes not present in our idealized model. Pythia automatically generates collision events with correlations for many different values of k and n for all allowed values of large n. Are there any questions? Well, I'm stupid. You can stop.